exponents. And, well, powers are a term that's often conflated with exponents, but actually, the exponent is the superscripted part. Like we say 4 to the power of 3, or 4 exponents 3. A number that's expressed using an exponent is a power. So technically, this whole thing is a power, even though you hear stuff like, 10 to the power of 5, or 10 to the 5th power all the time. So people can often be pretty fuzzy about terminology. The whole thing is a power. It has a base and an exponent, which is written as a superscript. Okay, so 4 to the power of 3, for example, is 4 times 4 times 4. There are 3 4s being multiplied together. So the base to some exponent is equal to a number of bases being multiplied together, and that number is equal to the exponent. So let's write these expressions using exponents. 10 times 10 times 10 times 10 times 10. How many 10s do we have multiplied together? Well, we have 5 10s, so 10 to the 5th power. P plus 2 times P plus 2 times P plus 2, well, the thing that's being multiplied together, i.e. the base, is P plus 2, and it's being multiplied together 3 times. So it's to the 3rd power. Expressions involving powers are evaluated using order of operations. Powers are repeated multiplications. However, exponents come before division and multiplication in priority because, well, exponents can also be treated as technically being bracket exponent. So, yeah, they have priority. So, they are evaluated after grouping symbols, so after any other grouping symbols, and before other multiplication or divisions. I mean, you could say that x was equal to a plus b or something, and then, yeah, if you substitute in, that is in brackets. If you take it to some exponent afterward. Or multiply it by something. So, evaluate x squared minus 4 if x is equal to negative 6. Well, that's equal to negative 6 squared, so we just substitute right in, and then we simplify. Negative 6 squared is, negative signs cancel out, 6 times 6 is 36, minus 4 gives us 32. Exercises. Write each expression using exponents. Well, the first question here is negative 5 times negative 5 times negative 5. How many negative 5s are there? I mean, we know that it's negative 5s multiplying together. Okay, and how many of them are there? There are 3. Here we have 3 x's and a y. So x multiplied by itself 3 times y. Z minus 1 is what's being multiplied by itself here. So that's z minus 1. And how many times does it occur? It occurs twice. Oh, by the way, if you don't see an exponent, that means it's an exponent of 1. So this is x to the 3rd, y to the 1st, technically, because there's 1y here, as you can see. Down here, we're going to have 9 times negative t times negative t times negative t. So, what's this thing that's being multiplied by itself? Oh, it's negative t. And there's how many of it? There's 3 of it. And 9 is the coefficient in front. The constant number that's being multiplied in. Since we aren't being told to treat the 9 like 3 times 3, we don't change it to say 3 squared. If this had been given as 3 times 3 times negative t times negative t times negative t, that would have been 3 squared and then negative t to the third. Evaluate each expression if g equals 3, h equals negative 1, and m equals 9. G squared minus m, well, that's 3 squared minus 9, which is equal to 9 minus 9, which is equal to 0. Okay, h squared minus g, well, that's negative 1 squared minus g, which is 3. Negative 1 times itself is, the negatives cancel out and it's just 1. So minus 3 is equal to negative 2. G to the third minus 2h. But that's 3 to the third minus 2 times negative 1. So 3 to the third is 27. Because 3 times 3 is 9. 3 times 9 is 27. Minus 2 times negative 1. Well, that would be minus negative 2, or just plus 2, because there's a subtraction, or addition, so a lower priority in between. You can do it from both sides at once. So 27 plus 2 is 29. M plus hg squared. M is 9. Plus h is negative 1, and g is 3 squared. So that is going to be 9 minus this. An exponent is a multiplication. So what happens if you have more things multiplied in at the same time? Well, by the associative property of multiplication, you can multiply them all at once in whatever order. So, negative 1 times 9 is, of course, going to be negative 9, but since it's a plus sign here, well, opening of the bracket just doesn't change the signs inside, so it's minus 9. 9 plus negative 9 is 9 minus 9, so it's 0. A prime number has two factors, so two whole numbers that divide it to give you a whole number as a result. The two factors are 1 and the number itself, because dividing by 1 gives you your original number, and dividing by itself gives you 1. Now, a composite number has more than two factors. 0 and 1 are neither prime nor composite. And there's only one even prime number, which is 2. Okay, determine whether 31 is prime or composite. What numbers can divide 31? Well, if you notice something, if you have factors of, say, some number n, it's going to be equal to 1 times n, and then 2 times n over 2, maybe. I mean, technically it's always true, but I mean as factors. Probably should spell maybe with a space then. Anyway, so you could have 2 times n over 2. You could have 3 times n over 3, and so on and so forth. But you'll find that they always make pairs. Factors paired. Unless n equals x squared, where x is some integer. For example, 4. You have 1 times 4, and then you have 2 times 2. So, You're going to have pairs of factors. What does that mean? That means you go 1 and n, and then, well, square root n may or may not be involved, like 2 and n over 2. So you pair them up, and you may or may not get a square root n in the middle, but they're paired up across where square root n is. So what's the square root of 31? Well, it's between 25 and 36, so the square root is between 5 and 6. Okay, then. Square root 31 is between 5 and 6. So test. You only have to test 2, 3, 4, and 5. So in other words, besides 1, the numbers up to the square root. More specifically, you only need to test the prime numbers up to the square root, because the composite numbers, well, if it was divisible by 4, it would already be divisible by 2. So really, you only need to test the prime numbers. Primes up to square root 31 to see if any can divide this. Divide 31. Conclusion is, of course, no. 31 is not divisible by 2, 3, or 5. No. Thus, it's prime. Now let's say we want to find the prime factorization of 48. The prime factorization is when you write out all the prime factors with suitable exponents which multiply out to equal the number you're looking for. A factor tree can be used to find the prime factorization. A factor tree would look like this. 48, 8, 6, 2 and 3, 2 and 4, and 2 and 2. The method I prefer, because this does not concentrate all your prime factors on the same level, okay? That's one of the issues I have with factor trees. The method I prefer is inverted division. So 48, okay, we see that it's even. The last digit is even, so divide by 2. 24. Oh, it's still even, so we divide by 2 again, and we get 12. And it's still even, so we divide by 2 again, and we get 6. That's still even, so divide by 2 again, and we get 3. Okay, then. This shows you that you have 48 equals 2 to the 4th power times 3. Which is a little bit less messy than this, in my opinion. It's also considerably less writing, as far as I can tell. It takes up much, much less space on your page. In algebra, monomials can be factored as a product of prime numbers and variables with no exponent greater than 1. What does that mean? Well, that means 7x to the 2.9 is going to be 7 times x times x. I'm not going to use the dot product notation here on this board because it's kind of hard for you to see. And then x to the 0.9. Yeah, by the time you get to dealing with fractional or decimal exponents, you're probably not doing this sort of factorization much. But, well, now we know that none of the exponents are supposed to be greater than 1. Hurrah. So factor 729k to the third. Well, what's 729? 729. Is it divisible by 3? Well, the digits add up to 18, so yeah, it's divisible by 3. And that gives us 243. Divide by 3 again for 81. Divide by 3 again for 27. Divide by 3 again for 9. And divide by 3 again for 3. So it's 3 to the 6th power, k to the 3rd power. Now this is a prime factored way of writing this. Kind of like up here where we had the prime factors and their exponents, except here we also have variables and their exponents. If you want to write it out the long way instead, you're going to end up with, well, something pretty long. By 3, by 3, by 3, by 3. So a total of 6 3's times k, times k, times k. So there's 3 k's as per the exponent. Alright, exercises. Determine whether each number is prime or composite. Well, 27. Can we factor this? Oh, the digits add up to 9, which is divisible by 3. So, okay. 9, and we divide again. Oh, we get this. So 27 is equal to 3 to the 3rd. Therefore, it is composite. Because it has factors other than 1 and itself. 151. Well, the square root of 151 is going to be between 12 and 13. Because 12 squared is 144, 13 squared is 169. So, we got to test primes less than 151 for division. Our conclusion is that it's not divisible by 2, 3, 5, 7, and 11. Which means that thus 151 is prime. Because factors will come in pairs unless the number is a perfect square. And if it's divisible by a composite factor that's less than its square root, then it would have been divisible by one or more prime factors already that are less than its square root. Like say a number is divisible by 12. Well, that tells you that it's divisible by 2 and by 3. If a number is divisible by 4 or 8, well, that tells you it's divisible by 2. Since it's not divisible by any of the prime factors that are less than its square root, there are no other pairs of factors that multiply to produce it, that are integers at least, besides itself and 1. Okay, write the prime factorization for each number. Use exponents for repeated factors. Well, 16 is, you see that it's divisible by 2 first. So we end up with 8, 4, 2, and 2. 16 is equal to 2 to the 4th power. 78, well, we factor it, and we end up with 39, and then, oh, that's divisible by 3. It's 13 times 3, to be specific. So, that's equal to 2 times 3 times 13. All of them are to the first power, so the exponents are 1, and we don't need to write them. Factor each monomial. 12m to the third. Well, we know that 12 is 2 times 2 times 3. So maybe 2 squared times 3 times m to the third. Or just 2 times 2 times 3 times m times m times m. Negative 10 kh to the third. Well, negative 10 is negative 1 times 2 times 5. 2 times 5 times k times h times h times h again. Yeah. A squared bc to the third. Yeah, it's pretty obvious that this factor, the monomial, does not mean your usual version of prime factorization. So it's not just going to be prime factors and exponents and variables and their exponents. No, I'm pretty sure this is supposed to be written out the long way. There's 2 a's, because a is to the power of 2. There's 1 b, and there are 3 c's. And 8, 49er. 49R. Well, 49 is 7 by 7, as I hope we remember from our times tables. So 7 times 7 times R. The greatest number that is a factor of 2 or more numbers at the same time is the greatest common factor of those numbers. 2 ways to find the GCF are shown below. In other words, I'm going to show them here. You could list factors. List factors. Or, what else could you do? Well, you could use prime factorization. What happens if you list factors? Listing gives us 1. For 24, we get 1, 2, 3, 4, 6, 8, 12, 24. So, what about 32? Well, we get 1, 2, 4, 8, 16, 32. Well, what do we see? Oh, we see that 8 is the largest number shared, so GCF is equal to 8. All right, what else could we do? We could also use prime factors. The prime factorization method, 24 divided by 2, 12 divided by 2 again, I get 6, and divided by 2 again to get 3. Okay, and then 32 divided by 2, 16 divided by 2, 8 divided by 2, 4 divided by 2 again, 2. Okay, so 24 is equal to 2 to the third times 3, and 32 is equal to 2 to the fifth. Largest shared prime factor and exponent factor and exponent is therefore, well, here we have a 2 to the third power. That will be able to divide 2 to the fifth power. But 2 to the fourth power cannot be divided evenly here. So 2 goes up to the third power at most. So, I mean, technically it's prime factors and exponents, as in plural, but because we don't have 8 times 3 to the second or something over here, we can't include the 3. So the largest shared prime factors and exponents give you your GCF equals 2 to the third. Your greatest common factor is 2 to the third. In algebra, greatest common factors can be used to factor expressions. For example, let's factor 4x plus 10. Well, 4 is 2 times 2, 10 is 2 times 5, so the greatest common factor is 2. 2 times 2x plus 5. Exercises. Find the greatest common factor of each set of numbers. 30 and 42. Well, 30 divided by 2, 15 divided by 3 is 5. 42 divided by 2 is 21. Divided by 3 is 7. So 30 equals 2 times 3 times 5. 42 equals 2 times 3 times 7. GCF is equal to 2 times 3. Or if a numerical value is insisted upon, 6. Okay, 15 and 33. We don't actually have to do the factoring thing here because we know that 15 is 3 times 5. So 15 equals 3 times 5. And 33 is equal to 3 times 11. The GCF is therefore, well, there's no 5 or 11 shared, but there is a 3. Specifically, a 3 to the power of 1. Shared. Now 44 and 110. 44 is equal to 2 squared times 11. It's 4 times 11. So 110 is 10 times 11. In other words, 2 times 5 times 11. So the greatest common factor is equal to 2. Like, you only have 1 2 that's shared. The other one is 2 times 2. But you can't divide 110 by 4 and get away with it. So it's just the lowest exponent of a shared prime factor. And 5 is not shared, so it's not here. And the lowest exponent of 11 and 11 is 11 equals 22. Let's factor these expressions here. 3d minus 6. Well, 3d is a multiple of 3. And minus 6, well, that's also a multiple of 3. So this is distributive property in reverse. We know that by distributive property, we can open up the bracket and multiply the 3 into each item. So 3d, and then 3 and negative 2, so minus 6, right? So we go in reverse, and we factor out a 3, because that's the greatest common factor between 3d and negative 6. There's no bigger number that divides both of these. Well, okay, if you say that let d equal some value, maybe. But as is, with just d being an unknown variable, no, there's no bigger option. All right, 6a plus 18. 6a is divisible by 6, and 18 is divisible by 6. The first choice you want to look at for greatest common factor is the coefficient of the variable. If that divides the constant term, or if the constant term divides the coefficient of the variable, it's pretty easy to factor out. Like if you get 4x plus 2, yeah, guys, you're going to end up with 2 times 2x plus 1. Here it's going to be 6 and a plus 3. F squared plus 4f. Well, we can't do anything about the coefficients because the coefficient here is 1. So what about the variables? Oh, hey, both of these are multiples of f. So it's f times f plus 4. F times f is f squared, and f times 4 is 4f. 6 minus 3j. Well, 6. No, you can't divide 3 by 6 and end up with a whole number, but you can divide 6 by 3. So, you get 3 times 2 minus j. You don't need to factor out in a way that makes the coefficient of your variable inside the bracket positive. Like the signs don't actually matter. I could have factored this out as negative 3 times negative 2 plus j. But the order it's written in, no, this is better. We just divide by 3. 16n squared minus 40n. Yeah, it's usually the case that when you factor out a positive number, unless you're specifically trying to cancel a negative number somewhere else, in which case, yeah, you can do this. Like if you're doing, say, a fraction, and the bottom is negative, and you want to factor out something that's also a negative, okay, and then you can cancel them. So 16n squared minus 40n. Well, 16 is 8 by 2, and 40 is 8 by 5. So, we got an 8 as a common factor, specifically the greatest common factor. And we also got n squared versus n, so we can factor out an 8 and an n. What happens if you divide 16n squared by 8n? You get 2n. And then minus 40n divided by 8n becomes minus 5. Because negative 5 times 8n is equal to negative 40n. Simplifying algebraic fractions. A fraction is in simplest form when the greatest common factor between numerator and denominator is 1. In other words, we've canceled out all the common factors we can, besides 1, which we can't help. One way to write a fraction in simplest form is to write the prime factorizations out and then cancel the terms that match up. In other words, you divide both by the greatest common factor. For example, write 16 over 24 in simplest form. Well, 16 is 2 to the 4th power. So 2 to the 4th power. 24 is 3 times 8, as in 2 to the 3rd power times 3. And what can you do here? Oh, you can cancel out 3 of the 2's. And you end up with equals 2 over 3. So yeah, that's how it works. Algebraic fractions can also be written in simplest form. For example, if you have 30ab squared over 36a squared, well, you write out the factorizations, which come out to 5 times 6 is 30. 6 times 6 is 36. Yes, okay, that's obvious, but the standard method is to write out the prime factorizations, even if it seems kind of obvious. So, 5 times 6 is 2 times 3 times 5, and then times ab squared. Over, because I am not going to write out times a times b times b. No, we can just cancel the exponents as needed, guys. So, 36 is 4 by 9, or 6 by 6. So 4 by 9 gives us 2 squared times 3 squared times a squared. I wonder what we can cancel. Oh, we can cancel a 2, we can cancel a 3, and we can cancel an a. The result, 5b squared over 2 by 3 by a, so 6a. Given this question's relatively small numbers, you could easily have just crossed out and canceled a 6 right away, and then canceled an a as well. And then just one line equals, instead of writing the prime factorization. However, the difference is that no matter how big your numbers are, prime factorization and then canceling always works. It's harder to make a mistake. And of course, if you need, feel free to actually write out the prime factorizations like this. Okay? Like, there's no problem with taking up more space on a page. The problem is if you get it wrong. Alright, exercises. Simplify each fraction. If it's already in simplest form, write simplified. Well, 14 over 22 is equal to 2 by 7 over 2 by 11. So we can cancel and get 7 over 11. 75 over 100 is 3 by 25. In other words, 3 by 5 squared over 4 by 5 squared, so 4 by 25. That's 2 squared by 5 squared. These cancel, and we end up with 3 over 4. Now 6 over 14, 6 is 2 times 3. 14 is 2 times 7. So we can cancel out the 2's, and we end up with 3 over 7. 3 over 8, on the other hand, we have 3 over 2 to the third power. So it's already simplified. So simplified. C over c to the fourth power. Well, cancel that out to a 1 and cancel the 4 out to a 3. So you get 1 over c to the third power. 15b over 27b. 15 is 3 by 5 times b. Over 27 is 3 by 9. So that's going to be 3 by 3 by 3, so 3 to the third power, times b. Now we can cancel this to a 2, which leaves us with, the b's also cancel. That leaves us with 5 over 3 squared, or 5 over 9. How about 24w over 30j? Well, 24 is 3 times 8. In other words, 3 times 2 to the third times W. 30 is 5 times 6. So 2 times 3 times 5 times J. Okay, 2 cancels a bit. And then the 3's cancel away. And that's it. So we end up with 2 squared W over 5J. Or, if you like, 4W over 5J. 9D squared over 6D. Well, we know that 6 is 2 times 3. And 9 is 3 squared. And times D squared. And here times D. We treat a variable like we would treat a prime factor. So we cancel out a D, and we cancel out a 3, and we end up with 3D over 2. Oh, yes. What happens when you multiply monomials? Monomials just means single terms, like say a to the 5th power, or a to the 6th power, or a to the mth power. Well, if you have the same base and you're multiplying powers, you just add the exponents. Why is this? It's shown up here. What is a power? Oh, it's a base multiplied to itself the exponent number of times. So a to the power of m is m a's all multiplied together. And then if you multiply by a to the power of n, i.e. n a's all multiplied together, what do you get? Oh, you get a total of m plus n a's multiplied together. That's why when you multiply powers that have the same base, the exponents get added together. For example, 4 squared times 4 to the 5th is equal to 4 to the power of 2 plus 5, which is 7. When you divide powers with the same base, you subtract the exponents. Why? Oh, hey, if we have a bunch of a's, like say 4 of them, and then we divide by 2 of them, we cancel out, which leaves us with 4 minus 2 a's. So let's do some examples. 2a squared times 3a. Express your answer using exponents. Well, we know that the coefficients multiply together separately. So 2 times 3 is 6, and then a to the power of 2 times a to the power of 1. So we end up with how many a's multiplied together? 2 and 1. So 2 and 1 is 3 a's. 6a to the third. Find negative h to the 4th over negative h squared. Express your answer using exponents. Well, the base is negative 8, and the new exponent is going to be 4 minus 2, which gives us negative 8 to the power of 2. It says express the answer using exponents, hence why we're not simplifying. Exercises. Find each product or quotient. Express your answer using exponents. F to the 3rd times f to the 6th is going to be equal to, the base is f, and the exponent is, well, there's 3 f's and there's 6 f's put together. There's how many f's multiplied together? It's 3 plus 6. In other words, f to the 9th power. Negative 5x squared times 6x to the 3rd. Well, negative 5 times 6 is going to be negative 30. And then it's going to be x 2 plus 3, because it's x squared times x to the 3rd. So that's going to be negative 30 x to the 5th. Alright. Negative 10 to the 3rd over negative 10 to the 3rd. Well, anything divided by itself, except for 0, is going to be 1. But if we're expressing it using exponents, we have negative 10 to the power of 3 minus 3. So in other words, negative 10 to the 0th power. A number that's not 0 to the 0th power is equal to 1. This has implications, guys, which we'll discuss shortly. Negative d to the 16th over negative d to the 12th. Well, the base is negative d, the exponents, 16 minus 12. So negative d to the power of 4. Negative 5m to the 3rd times 4m to the 6th. Well, the coefficients are multiplied together, so negative 20 and m to the 3 plus 6. So negative 20 m to the 9th. The product of 2 cubed and 2 squared, well, that's 2 to the 3rd times 2 squared, which is equal to 2 to the 3 plus 2, which is 2 to the 5th. The quotient of 6 to the 8th power and 6 squared. That's 6 to the 8th power divided by 6 squared. So we're dealing with 6 to the power of 8 minus 2 equals 6 to the power of 6. Yeah, so that's how multiplying and dividing powers with the same base works. And what happens if they're not the same base? Like say you got 6 to the something's power and 9 to the something's power. Well, how do they relate? Oh, you can do prime factorization and then multiply together the prime factorized versions and you end up with a prime factorized number that's the product of the two. When you have something to the power of 0, you end up with 1. Well, there's a pattern. Like say 4 squared is equal to 16, 4 to the 1st power is equal to 4, 4 to the 0th power is equal to 1. So you divide by 4 each time. Okay, this makes sense. What happens when you have 4 to the negative 1st power? Well, if you divide by 4 again, you end up with 1 over 4. Like what happens when you get 4 to the 1st power divided by 4 to the 2nd power? Oh, you get 4 to the 1 minus 2 power, which is equal to 4 to the negative 1st. And yet we can clearly see that here we can cancel this and end up with 1 over 4. So 1 over 4 is equal to 4 to the negative 1st power. For a to the power of negative n, if a is not equal to 0, then a to the power of negative n is equal to 1 over a to the power of n. So in other words, a negative exponent just means you gotta go 1 over the base to the exponent now made positive. Like say we have 2 to the negative 4th power. Well, that is equal to 1 over 2 to the 4th power. U to the negative 238th power is equal to 1 over u to the 238th power. So we just take off the negative symbol and then put it as a denominator. and 1 as the numerator, right? Well, actually, no. What if it was a squared u to the negative 238th? Well, a squared would be the numerator then. So u to the negative 238th just means you have u to the 238th in the denominator. We can evaluate algebraic expressions with negative exponents using the definition of negative exponents. Evaluate b to the negative second power if b equals 5. Well, b to the negative second, first of all, that equals 1 over b squared. And b equals 5, so 1 over 5 squared equals 1 over 25. Now let's write each of these expressions using a positive exponent. In other words, they're going to get moved down to denominators. 2 to the negative fourth power is equal to 1 over 2 to the fourth power. Negative 7 to the negative eighth power is equal to 1 over negative 7 to the eighth power. J to the negative fifth power is 1 over j to the fifth power. Let's write each of these fractions as an expression using a negative exponent other than negative 1. So, in other words, you're not allowed to simplify first. You can't go, oh, 1 over 2 to the third is 1 over 8, therefore it's equal to 8 to the negative first power. No. So we're dealing with 2 to the negative third power is equal to 1 over 2 to the third. 11 to the negative fourth power is equal to 1 over 11 to the fourth power. Here, 1 over 23 to the fifth power is equal to 23 to the negative fifth power. Now let's evaluate each of these expressions if m equals negative 2, n equals 2, and p equals 3. So, m to the negative 4 is equal to 1 over m to the fourth, and now we substitute in. That gives us negative 2 to the fourth, and 1 as a numerator. Okay. Negative 2 to the fourth power, there's 4 negative symbols, so they cancel out, and 2 to the fourth power is going to end up giving you 16. 1 over 16. np to the negative first power, that's 2 times 3 to the negative first power, so 1 over 6. 3m, well, that's 3 times m, which is negative 2, so negative 6. Yeah, so you just substitute in as usual. You can do some rearrangements before substituting, or you could have substituted and then rearranged. It's fine either way. But of course, you must follow order of operations. Scientific notation. Numbers like 5 million or 0.0005 are in standard form because they do not contain exponents. But if you're dealing with large numbers or really small numbers, it's convenient to use scientific notation. And scientific notation is written as a number that's between 1 and 10. It could be 1, but it can't be 10, because otherwise you end up moving the decimal place over another one and increasing the 10 to the power of n by, well, it's going to end up being 10 to the power of n plus 1 then. So, you have a factor multiplied by a power of 10. And the power of 10 must be an integer power of 10. So it must be 10 to a whole number exponent. In other words, this dictates where your number is. So say all these placeholder digits, this is 10 to the 6, and then in front we have a 5. 5 times 10 to the 6. So 5 times 1 million is equal to 5 million. And here, well, 10 to the 0th power is the units digit, 10 to the negative 1st, negative 2nd, negative 3rd, negative 4th. So 10 to the negative 4th. And what's there? Oh, it's 5. Starting at the 10 to the negative 4th digit, we have a 5 in that decimal. So let's express each of these numbers in standard form. 5.01 times 10 to the 6. Well, what does this tell us? Oh, it's also equal to, you can think of it as, 501 times 10 to the 4th. How did we do that? Well, we took 10 to the 6 and we broke it up into 10 squared times 10 to the 4th. And we use the 10 squared, i.e. 100, to multiply the 501 to give us an actual whole number instead of 5.01. So, you could think of it like this. There's no issue with this way. So what does this do? Oh, you get 501 and 10 to the 4th is 4 zeros. And then you can put the commas in to mark the place if you go by the English convention of commas for placeholders. Well, place markers. So, how else could you do this? Oh, you can go, I know I have 6 digits after the 5. So 6 digits, 1, 2, 3, 4, and we know that there's a 0, 1 over here, and then it's a 5. So 6 digits. Now 3.08 times 10 to the negative 5. Well, you would start by going 10 to the 0th, 10 to the negative 1st, negative 2nd, negative 3rd, negative 4th, and then on the negative 5th, you put your number. You write it out, starting with its units digit. Because what this means is 3.08 times 0.00001. Yeah, that's just going to replace the 1 with the 3 and then add the rest of your amount after. Okay. Express each of these numbers in scientific notation. 209,000,000. Well, it's going to be 2.09 times 10 to the what? Oh, there's 1, 2, 3, 4, 5, 6, 7, 8 digits after the 2. So after the leading digit, there are 8 digits. That means 10 to the 8th. Here, though, we have to go 10 to the 0th, negative 1, negative 2, negative 3, negative 4, negative 5, negative 6. So 10 to the negative 6 to get us to this position. And then it'll be 3.208. 3.208 is the numbers that are not just placeholders. All right, exercises. Write these in standard form. 1.2 times 10 to the 6. Well, 1, 2, and then we know that there are 6 digits after the 1, so this is the first one. Second, third, fourth, fifth, sixth. Okay, so there's 6 digits after the 1 now. Great. And the numbers where we actually have information are filled in, and the rest are placeholders. 5.8 times 10 squared, well, that's 5.8 times 100, so 580. Yeah, we should probably put an equal sign over here too. So 9.01 times 10 to the negative third. Well, we know that it's going to be 10 to the 0th, negative 1, negative 2, and on the negative 3 we got the 9, and then 01. Express each number in scientific notation. This one we got 10 to the negative first, second, third, fourth, fifth. So it's going to be 10 to the negative fifth. And then 7.463. Okay then. 235,000, so 235,000. We got a 2.35 in front. And then multiplied by, there are 5 digits after the 2. So 10 to the 5th to get it to the right place. 0.00377. Well, that's equal to 3.77 times 10 to the negative how many? Well, negative third would be the third 0. Now, that 3 is therefore in the negative fourth. 10 to the negative fourth position. Choose the greater number in each pair. Well, this 901 is a result. 9.01 times 10 to the second is just 9.01 times 100. So it's 901 verse 910. So 910 is greater than 9.01 times 10 to the second power. Here we got 0.000091 and 3.9 times 10 to the negative 4. Well, here that's equal to 9.1 times 10 to the negative first, second, third, fourth, fifth. 10 to the negative fifth verse 3.9 times 10 to the negative fourth. 10 to the negative fifth is less than 10 to the negative fourth. And since these are normal scientific notation where it's between, including 1, and strictly less than 10, that means the 10 to the negative fourth one is going to be larger. 3.9 times 10 to the negative fourth. 3.9 times 10 to the negative fourth is also equal to 39 times 10 to the negative fifth, which is of course going to be bigger than 9.1 times 10 to the negative fifth. Right? So, for this, with the way that it's written, you should probably write it like this. Yeah, you should probably write it the way it was written in the problem when you're asked to do comparison questions. Just saying, guys. So, that's it for this chapter on exponents. Well, see you next chapter.